what we've done so far? Based on the some of the questions that I had in the previous classes, I want to make a few points because there seems to be some confusion. One of the questions is about the issues of convergence. So people asked about what happens when epsilon equals 1, because we are interested in 3 dimensions. So we should put epsilon equals 1 and what happens. So the answer to that is we don't really know. In any non-trivial field theory, any field theory that's in some sense has to do with nature, which is sufficiently non-trivial, you won't be able to say anything about, well, it's very unlikely that you'll be able to say anything concrete about issues of convergence. So the fact that epsilon equals, we were doing an expansion in powers of epsilon, and we said epsilon is very small, it's a good approximation, and then someone said what happens when epsilon equals 1. The answer is it's not a good series because epsilon is much smaller than 1. It's a good series because the powers of epsilon are accompanied by small numbers. Typically, for instance, the anomalous dimension, when you calculate it, comes out like that. So this 1 over 54, it's a pure number that comes out of the calculation, is what makes this reliable. Okay. To take a more famous example, if you take quantum electrodynamics, as I was saying last time, E is 0.3. 0.3, the reason quantum electrodynamics gives you a good, nice answer that you can compare with experiment is not because E is 0.3. 0.3 is not really a small number. The reason is that the expansion usually comes in factors of E squared by 4 pi squared and so on like that. You get extra powers of, it's typically E squared by 4 pi squared or 8 pi squared that comes. And it's these factors of 4 pi actually that make the series give you numbers that agrees to the experiment. Now if you ask me what is the radius of convergence of this series, the answer is 0. Okay. In fact, there's a famous argument, I should have mentioned it, due to Dyson. Dyson points out that if you make E squared negative, arbitrarily small negative, the series, it's a sick theory. Because E squared negative means the charge is complex. So the theory is unstable. In fact, light charges will attract, you'll have a complete chaos. So for E squared arbitrarily small and negative, the theory is sick. So you can easily conclude that the radius of convergence is 0. Nevertheless, QED gives you a very good series in terms of actual numbers. 0. I'm giving an argument that it's 0, that it had to be 0, without knowing anything about the nature of the expansion. For E squared arbitrarily negative, the theory makes no sense. So the radius of convergence had to be 0. Now you can go and verify that it's actually 0 by actual calculation. And that's the same thing with epsilon. So the reason you get good numbers is not because epsilon is small or 1 or anything. It has to do with all these numbers, and that you don't have a way of predicting without actually doing the calculation. Okay. So in any non-trivial field theory, that little bit of guesswork has to be there. What is a good parameter? And then ultimately you have to, at the level of technology now, it's just a matter of trial and error. See if it gives a good series. You can maybe compare it with numerical work, lattice, and so on, or experiment and see if it works. Okay, so that's one point I wanted to make. So the issue of convergence. So the bottom line is it's not convergent. Okay, the question is whether it's a good, it gives you good numbers in the first few orders of perturbation or not. At some point it's going to break down. Yeah, the other point I wanted to make was there were questions about this figure I was drawing, and I had trajectories like this. And someone was asking me whether as you go along the trajectory, are you approaching the critical surface? No, this figure looks like that, but that's not true. Whether you're at the critical surface or not is decided by your initial Hamiltonian H0. Okay. So there is some temperature some parameter t that you define, which fixes for any value of u naught the value of r, or the other way around, which decides which trajectory you're going to be on. For a given t, there is a given correlation length. That's fixed. So along this trajectory, it's not as if you're approaching the critical surface and the correlation length is becoming larger. No, the correlation length is fixed once h naught is fixed. So this is a misleading figure. It's not getting more critical as you go in this direction. Criticality is fixed by the t. Either t equals tc or it's not, and then the parameter is t minus tc. So what happens as you go here is you approach this fixed point value. The values of the coupling approach the fixed point value. And therefore, for large number of iterations, you can do your calculations using this Hamiltonian. So that's the meaning of this approach, okay? That you can use this Hamiltonian to do your calculations. And that was the whole, so this idea that the fixed point can be used is important for so this is a statement of universality, that regardless of where you are, ultimately it's this Hamiltonian, which has no free parameters, that decides the physics. This idea was Wilson's main contribution, and based on that he built up this entire formalism, the idea of the fixed point. So these were two comments I wanted to make, and one more comment I want to make is this. This fixed point we drew was the Wilson-Fisher fixed point, and here remember there were two eigenvalues. One was greater than 1, one was less than 1. So you tune the variation corresponding to the greater one to 0, and then you stay on the critical surface. And then the smaller the one that gets smaller, takes you towards the fixed point. So conversely, if you're a little bit away, initially the growing eigenvalue has been suppressed because you tune t equals tc, and then you go near. But at some point, the growing eigenvalue takes over, and then you start to deviate. So this is the picture. On the other hand, there's another fixed point, which is here, which is the Gaussian fixed point. This is a trivial fixed point with u equals 0, u star equals 0, r star equals 0. Okay. Here, if you're in d less than 4, both eigenvalues are positive. Okay. So any perturbation in either u or r will take you away from the fixed point, and in general it will go off somewhere, but in particular you can tune it so it goes along this trajectory. Okay. So in this example, then there is a trajectory that connects this fixed point to that fixed point. It's a very special trajectory where you've tuned two parameters to connect like that. Okay. So this kind of issues, these kind of issues will become important when we talk about multiple fixed points later on. So I just want to keep this in mind. But what I want to talk today about is infinite. Yeah.
So the lattice size should not matter.
Yes.
So you should be able to describe them with a continuum theory.
Yes.
What about all along the trajectory?
So in fact, that today I'm going to talk about the continuum limit. The crucial point is not to be at the fixed point, but you should be at the critical surface. You don't have to be at the fixed point. If you're at the critical surface, you can define a continuum theory.
So all along the trajectory, psi is infinity.
Yes. Well, in this particular example, this one happens to lie on this critical surface. There's a fixed point. But in general, even if you didn't know about this, there is some critical surface, and you can define the continuum theory on that surface.
So
Yeah.
all along this critical
Yes. Yeah.
psi is infinity.
Yes. Yes. So in fact, so today that is precisely what I want to talk about. I want to talk about the switch from lattice condensed matter to field theory, where my aim is to take lambda naught to infinity. That's a continuum limit. So let's talk about that. It's actually a very simple thing, but it's very easy to get confused because of all these different scales and all that. So let me just write down a few points systematically before I come to this discussion. So our aim is to do that. Okay, so let me write that there. So I'll just make a few points just to be systematic. So part of it is a summary. Remember that our equation we're starting with is this. This is our starting point. What is HT? So again, of course, not everything that I say here will be directly relevant for the continuum limit, but for a general discussion of the RG, all these points you should know, at least you should see it once. So HT is an element of what Wilson calls the space S of all interactions. Okay, so this is the space of all Hamiltonians. So in the case of the spin 4 theory or spin theory, you had the Gaussian term, the U2, the U4, the U6, all those things, arbitrary values, define in this case the space of all Hamiltonians. So you start with H naught, which is in that space. You apply the RG many times, and you stay in that space. That defines the space of S. And we will write interactions in terms of dimension. So the interactions, which means the coupling constants, will be written in terms of dimensionless parameters. And the scale will be initially set by lambda naught. So in the case of the condensed matter system, we chose lambda naught and call it 1. Okay, but in general, now we are not going to hold lambda naught fixed in our new discussion, so I'll keep the parameter lambda naught. Okay. So all quantities, including momenta, distances, will be measured in units of lambda naught, parameters also. And this U, what is this operation U? U means integrate out. So this is what we did. So I'm just summarizing, integrate out Q, something like this, where Q now is P by lambda naught. I should say P by. And of course, remember we keep rescaling so that in the new theory, the cutoff changes, and you keep rescaling so that Q is always in this range. Okay, so that's important. So the physical cutoff in HT is e to the power of minus. So what we are doing is we're lambda naught, you iterate, integrate out half, and you make the scale lambda. It doesn't have to be half, because now remember we're doing it as a continuous change. So this lambda will be lambda naught e to the power of minus t. Okay, so the physical cutoff here is lambda. So your Hamiltonian HT has a physical cutoff whose value is lambda, which is smaller than lambda naught. Physical cutoff means what? All your momenta have to be less than lambda in physical units. Okay. And of course your Q again now will be measured in terms of P by lambda. Okay. What about the correlation length? So this is an important quantity. So to begin with, your H naught has some correlation length. What am I called it? Cp. So P stands for the physical length. Okay. Not in units of the cutoff, but the physical length. In HT, the correlation length Ct will be Cp times this lambda. This is remember this is a physical length, so it's in some meters or centimeters or something. So this is the dimensionless correlation length. So it's whatever your physical correlation length is times the value of the cutoff. The physical correlation length doesn't change. That's the correlation length of your system. Okay. Remember that's fixed by H naught. What I'm changing is the running cutoff lambda. So as lambda becomes smaller, this becomes smaller. Okay. And these are dimensionless, okay? So these are okay, so this is just some terminology. Just to be concrete, Wilson gives some examples. So for instance, your interaction, so example. So your interactions could be of the form x minus y squared times sx. So you can calculate something like this. So if you have a term like this in your Hamiltonian, that means the length, interaction length is of order 1 because the denominator is 1. Okay? In the units of your lattice, whatever it is. If you had a 0.001 here on the other hand, then the interaction length is much longer. Okay? So in this case, you would say that the range is about 1,000. If you had something like 1 over x minus y, this would mean the range is infinite. Okay, so this would mean range is order 1,000. This is just to be very concrete, nature of the Hamiltonian. And it's, okay, so now when we proceed, you can classify the surfaces in many ways, subspaces of S. One is classify by specify C. By the way, so when I do all this right now, I'm in a fixed value of lambda naught. I'm not yet taking the continuum limit or anything. So you're on a lattice with a fixed lambda naught and everything is in those units. So you specify C, define subspace. So C equals infinity specifies what is called the critical subspace. So typically, it's one number that you're tuning to infinity. So there's one constraint on your parameters. So this subspace will be one dimension less than the full subspace because you're tuning one parameter, which is the temperature. So if you have some number of relevant variables to tune, one linear combination will have to be tuned to get the critical subspace. Okay? So you can classify subspaces according to C. So you can have C equals 2, C equals 1, etc. Various.
Which is also the same as T minus TC.
It's a function of T minus TC. Yeah. So remember there's some critical exponent like that, which we've figured out. So you can plot this. If this is your space S, you can plot different subspaces like that. So this is, let's say, C equals infinite, so on. Typically, after you do your blocking, when you reach this subspace, you can stop. Because at that point, there are no non-local correlations. Your Hamiltonian describes the full thing. There's no correlation that beyond the scale of the Hamiltonian. So you're progressing like that. Okay. So this C is labeled by this parameter T. So if this is C naught, this is typically C will be e to the power of minus T times your original C naught. So now there's an important point he makes, which is the following, which is this. This is an interesting point. This HT. Now HT looks like a very complicated Hamiltonian because you started with H naught, you evolved and you got a very complicated Hamiltonian with all these U2s, U4s, U6 and all that. But it's actually very special. Why? Because what's special about it? Remember, each time you did the blocking, you got a local Hamiltonian. So HT, so if your initial Hamiltonian was local on the length scale lambda naught, this one is local on a length scale lambda, which is e to the power minus t lambda naught, or 1 over lambda. The length scale is 1 over lambda. Okay. So you have a Hamiltonian that's local on a length scale of 1 over lambda. Yeah, but the physics it describes is a local physics. It describes a physics where the original interactions are 1 over lambda naught. The locality is 1 over lambda naught. So imagine if you start with ht and work backwards. Okay, you have to typically, if you start with a Hamiltonian where the interactions are of order lambda, you work backwards. Say you go to lambda by 10, you're not going to get a Hamiltonian which is suddenly becoming very local. It's going to have the same interactions or more. I mean, same length or more. So ht work backwards has to give you an interaction with scale lambda naught. So in the space of all possible interactions, ht is very special. See, I hope you understand what I'm saying. This is a Hamiltonian whose scale, let's say, is 1000 times L naught, yet it's equivalent to a Hamiltonian where the scale is actually 1 or L naught. So it's a very special Hamiltonian that such that when evolved backwards, it will give you that special Hamiltonian. So these Hamiltonians are very special, although they look very complicated. They're actually very special. So one of the things you have to keep in mind when you define your theory is that the theory is actually very special. If it comes from a local scale, this theory is actually a very special theory. So you should not be surprised that you have to fine-tune a lot of parameters to get that original theory, such that when you go back, you get that theory. Okay, so now so this is just, so keep in mind these points, especially these notations. So remember that the scale, there is an important scale, the physical correlation length, which you can take in meters, let's say. Then there's a correlation length, dimensionless correlation length, which is times the value of the cutoff. And C naught is your original dimensionless correlation length. So in all our discussions so far, C naught was fixed and Cp was fixed because we didn't change lambda naught. But now we're going to change lambda naught. And the idea is you want to keep this fixed, not C naught fixed. This is what you want to keep fixed. One important point is that this thing doesn't depend on t. So there's translational invariance. Okay, so it's a property of these trajectories. So, so there is time translational invariance. So now I'm going to talk about the trajectories and how you time translational invariance. So your time t naught, you have C naught equals 1. So the dimensionless correlation length is defined to be, sorry, I'm choosing t naught, the time at which C naught becomes equal to 1. So that means Ct, okay. Why am I calling it time? Oh, just it's the form of an evolution. It's just just terminology. This is like a parameter that evolves in time. You can think of this as an evolution. Okay? What is evolving? It's the Hamiltonian that's evolving. So it's like a Schrodinger equation, except that what is evolving is the Hamiltonian itself. Okay. So I've chosen my, okay, well. So I'm going to choose my lambda. In other words, what I've done is I've chosen my lambda naught. So I have a whole series of lambda naught. I've chosen my lambda naught, so my initial C naught is just 1. Okay. Okay, now the fixed point, which is going to important, fixed point satisfies is h star such that u of h star equals 0. Okay. So as we said, either C star equals 0 or C star equals infinity at this fixed point. and both will become important. So these are two different kinds of fixed point. So what's the simplest topology of the flow, which is what we're going to use, is the following. So you have this manifold with C equals infinity. This is your critical surface, and so I have some fixed point P, which I call P infinity. And remember, on the critical surface, what happens is you flow towards the fixed point. And then you have a whole series of surfaces with smaller and smaller x's. So x equals 2, x equals 1, finally x equals 0, and here is the point P naught. Yes? Ah. Yes. Yes. Yeah. Yes. You mean limit cycles? In principle, that's possible. You're assuming, yeah. We're not saying it's the most general, but we're considering topologies like this. If you have limit cycles, you won't be able to take a continuum limit. It will be very complicated. I don't know actually. Don't know. So what are the possible trajectories? So one trajectory, I think this is a point, B, where you start from here and you flow to this. Okay. Then you can imagine starting from some point here and doing an RG and going to that, trajectory A. I just started an arbitrary point where, so this is your starting Hamiltonian, and I just flow like that. Because we know it has to flow to some fixed point, so this is, the things that flow to this are characterized by this surface. Any other thing will typically flow to that. This is the simplest topology. If you have more fixed points, it becomes more complicated. Then there's a trajectory, remember we call the renormalized trajectory, which is you start from here and you perturb it a little in a specific direction and you go towards that. So he's called this C. Okay. So this is the simplest topology that you can imagine, and the discussion will be based on this topology. So what is the nature of this? If you draw this, if you look at the stability, remember we found that the fixed point is stable in the sense that from here, typically you flow to this fixed point. Okay. On the other hand, if you perturb this trajectory, typically your trajectories deviate from that. Okay. So if you think in terms of a three-dimensional surface, what you expect that this trajectory is like a ridge on top of a mountain. Okay, so you have some. I'm not drawing this very well. I don't know how to draw this. So imagine you have a ridge like that, and you're flowing right at the top. So you're flowing like this. So this is the trajectory B. Okay. If you deviate from this on either side, you'll go away, because that's the nature of the. Remember the T not equal to Tc. It's a growing eigenvalue. So you just go away. Okay. Here, on the other hand, this is like a this is like a minimum. It's like a valley. If you start from here, you flow straight to that. It's from here typically all deviations will go to that. So it's like rolling down in a trough like that. So you're going like this on the top, and then you're on this. So here it's like a ridge. Here it's like a valley. So it's basically like a saddle point. In one direction it's curved this way, in the other direction it's curved that way. So a typical trajectory will go like that. It will be like this. It will go like that and then go off like that. Okay, that's a typical trajectory. A special tuned trajectory will be the one that goes there, and the more you tune, the more you go. Okay. Sorry? Simplest. Oh, because there's one fixed point with infinity, and you disturb it and it goes to a fixed point with 0. Because typically the correlation length decreases when you have a relevant perturbation. So it will typically go to 0. I mean, well, Yeah. If you have more fixed points, it's more complicated. This is about as simple as it gets. It has to start somewhere and go somewhere else. Yes, yes. Right. Yeah. So this is a surface C equals infinity. Remember, now we are in the lattice unit, so this is all in units of lambda naught. Okay? Or 1 lambda naught.
In the earlier example you did, both the Gaussian fixed point and the interacting fixed points are on psi equals infinity, right?
Yes.
And this was the...
This is the massive, yeah, where it goes off. Typically, you don't know. Huh? Well, this just means, what does this mean? This means that your theory is infinitely massive. There's no degrees of freedom. So if you have a massive theory, that's typically what. So if you have QCD with a mass gap, at low energies, everything is infinitely massive. There are no degrees of freedom. That's all. No, yeah. If you say, does it have to exist? Well, in this trivial sense, yeah.
I can see that the linearized analysis around the fixed point.
Yeah.
Or even the critical surface will tell you that there's one positive eigenvalue from
Right.
But does it have to end at a fixed point? Not seen from the linearized analysis around there.
Well, no, the fact that C gets smaller as you do the RG is trivial, is just dimensional analysis. So it has to get smaller. So eventually, if it hits 0,
What I'm worried about is if you say that's a fixed point,
yeah.
there should be a scale invariant theory.
No, but that's the point. This is a trivial fixed point. A scale invariant theory can be in a non-trivial way or in a trivial way. Non-trivial way is if there are degrees of massless degrees of freedom. That means C is infinite. This is a trivial where everything is infinitely heavy.
How do you make sure J equal to 1? It's by choosing the couplings.
No. Psi equals, see, this is, you're just starting from some psi and doing a block transfer. So I have a fixed Hamiltonian, lambda naught, and I'm just calculating as you do the this operation, where does my point flow? So typically psi of t is e to the power of minus t times psi of 0, just by dimensional analysis. So whatever your starting psi is, after you've done the blocking many times, your psi will get smaller and smaller and smaller, simply because you're blocking, that's all. So this is just that flow. I have not, lambda naught is fixed here.
J1, J0.
Yeah. Yeah.
They are corresponding to the H0, right? The starting point.
No. So you start with some H naught, it has some C naught, psi naught. Then you do the blocking, the psi gets smaller and smaller and smaller.
Can I choose the coupling such that the G0
Yeah.
is 0?
Z0 is 0 would mean that correlation lengths are 0. It's infinitely massive. So it will be like choosing R0 to infinity. Infinite. Yeah. Yes. No, that's what I said. So the parameter R gets bigger as you block. So if you don't tune it, it's going to go to infinity anyway, trivially. So that just means so okay, what does this mean physically? You have imagine free scalar theory. You have some massive scalar. As you go to lower and lower energies, that mass will appear to be much heavier than your energy. So at 0 energy, the scalar will appear to be infinitely massive. You have no degrees of freedom. So
Away from the critical surface,
yeah.
you have to describe it as a lattice model.
No. At this point, everything is a lattice model. I have not taken any continuum limit. So I have a lambda naught. Oh, okay. In the lattice model, you have a correlation length, which is, let's say, 1 in some units. Now, you change your units to 2, then the correlation length becomes half in the new units. Now, you choose your correlation length to be, the L naught to be 4 times what it was. Then your new correlation length in the new units is 1/4. So the larger and larger you make your lattice, the scale, the coarse graining you do, in those units, because you're always measuring in terms of your new lattice, which has been rescaled to 1. So in your new units, your correlation length gets smaller and smaller and smaller. So in the units, so you rescale your unit so your Hamiltonian always has interactions of length 1. But now that length 1 is a huge length, so your correlation is very small.
Was they infinitely so that you have forgotten about the original system completely and there's nothing there? Meaning the block size is the
Block size is so large that your correlation length in those units is practically 0. Yeah. So initially if your correlation length was 100 times the block size, now your correlation block size is so large, the correlation is 0 in those units. Yes, yeah, that's right. So this is all in terms of given Hamiltonian with a fixed lambda naught, how you flow. Yeah, and one other point which I will just make casually is that this is not immediately relevant for this, but the space S as t goes to infinity, this is a subspace. Each time you're getting into in some sense a smaller subspace because each one is inside the previous one. As t goes to infinity, you typically come to a very small special subspace, which is a very special set of interactions which you can get from any interaction as you go infinite number of rescaling. So things, the space of parameters shrinks and you get a smaller subspace. And another point about the fixed points, which also I mentioned earlier, is that in these trajectories you can take this example also. If you imagine a ball rolling, as you approach this, d by dt of h approaches 0 because at the fixed point it's exactly 0. So the speed of this ball rolling gets smaller and smaller as you approach this point. So you spend a lot of time in this region, okay, typically. And remember, this point we exploited in defining our correlation lengths and getting universality. So now, with this as background, we have to talk about how you're going to take, how you're going to do QFT. So in QFT, typically what you want to do in the simplest case is you want to get a theory with a physical correlation length. So one, we want to obtain finite theories So now I'm switching viewpoint. I'm saying we don't have a fixed lattice. Previously we had a fixed lattice and everything was units of that. I'm interested in the continuum theory, in quantum field theory. So I would like to take this lambda naught to infinity, okay? And in the process I want to get finite answers for correlation lengths. So you want to get finite theories as lambda naught goes to infinity. And ideally also obtain non-trivial theories with interaction. So start with phi-4 theory. Now I'm using continuum notation instead of sigma and s and all, I'm just calling phi. Phi-4 theory. Finite cutoff. So now we are using the continuum language. You can think of this lambda naught as a lattice, but it's some cutoff, and I want to take lambda naught to infinity. So I want to take such that these two theories hold, these 2 points hold. So first step to make this discussion, let's rescale and make lambda naught equal to 1. So we'll keep rescaling back and forth, so don't get confused. And use dimensionless momenta. This is what we were doing when we were working on the lattice. We were calling this as 1. Let's do that rescaling. So what are the two free parameters? Two free parameters a priori are the mass and are u naught and r naught. Okay. So in this space, there is something called the canonical surface. It's just a name. So the canonical surface is typically your H naught, the space of H naughts. What do I mean by that? What do you do in field theory? You start with a very simple H naught. So you write down phi box phi plus m squared phi squared plus lambda phi 4. Just two numbers, m and lambda. This is a very special subspace in the space of all possible interactions. That starting thing is typically what you call a canonical, it's just a word. Canonical surface will be a very simple thing, typically in terms of a few constant parameters. Okay. So I'm going to now draw a figure. So I think I will erase this. I'm going to draw the same kind of figure, but with some number of curves. So this is c equals infinity, c equals 0, this is p0, p infinity. So I'll draw some values. So let's say this is c equals 5, c equals 2, c equals 1. And so here I'm going to choose, let's say, so various values of, so let me draw a curve. This is what I call the canonical curve. So now I'm starting, my starting point is H naught and a lambda naught. Because now I'm going to talk about different values of lambda naught. So I have to specify for every lambda naught an H naught. This is this canonical, where typically this H naught will be some simple thing, like in this case just two coupling constants. Okay. So this is what I have to specify. Okay. So that's my, so I've drawn a curve like this, which I would call this curve is the canonical curve. Canonical, what is it called? Canonical curve HD of lambda naught. Okay. So what is this? This is a set of dimension, and HD is parameterized by dimensionless numbers. So it's a dimensionless parameters. So in the example at hand, we had U naught and R naught, which were dimensionless. Okay. But what I have to do is to specify some canonical curve like this. For every lambda naught, I have to specify some U and R naught. Okay. So what do I do? So here's an example I've taken. So here I've chosen c equals 5, lambda naught equals 10, c equals 2, lambda naught equals 4, like that. Okay. So let me explain this. So I choose R naught. So now I'm telling you how to choose this. R naught by lambda naught is mu naught squared, the naught squared, and U naught of lambda naught this is my choice. What have I done? I've introduced a parameter mu, which you can think of as the physical mass of the scalar field. Okay. And this dimensionless parameter is now mu naught squared by lambda naught squared. So you pick some mu naught squared that you want. Then for a given lambda naught squared, this dimensionless parameters are naught by lambda naught. Okay. Is this clear? It just means you're defining physical mass, some GV, and then you have to choose cutoff lambda naught. Whatever lambda naught you define will define a dimensionless R naught. And this is my end result that I want. So the question is, it's obvious from this how you should choose R naught with lambda naught, right? If I change lambda naught to 2 lambda naught and I hold mu fixed, then R naught has to become 1/4. When R naught becomes 1/4, your C will become half, or sorry, 2. The smaller R naught, the larger your C. Okay. So that's so here so let's see. So C is well, in terms of C. So C is proportional to, remember, 1 by square root of in the simplest case, just dimensional. For instance, in the Gaussian case, it goes as 1 by square root of R naught. But this is not the general case. But the point is, C will be inverse proportional to R naught. So if you typically, so let me put it this way. C is typically when the coupling constant is small, C will typically go like that. Okay? So this choice, I'm keeping my mu naught fixed. Okay? So as I said, this R naught will go roughly as 1 by C squared, right? Let's say in the free theory, dimensional reasons, R naught will go as 1 by C squared. So I've chosen, so you can see that C has to increase with lambda naught if you want to hold mu fixed. And that's just dimensional analysis. Okay? So that's what I've done here. So if I choose a given lambda naught equals 10, I need to choose C equals 5. If my lambda naught is 4, I need to choose C equals 2. If my lambda naught is 2, I need to choose C equals 1. So for any given lambda naught, I have to tune my R naught so that I get that C such that I get the given mu naught. So whatever lambda naught is, let's say U naught is fixed. Okay, U naught is, why am I saying U naught is fixed? Because typically in these theories, U naught goes to some fixed point value. So we won't even worry about that U naught. The one thing you have to tune. So you'll tune your R naught as a function of lambda naught so that this mu naught is fixed. So in other words, your lattice spacing, as your lattice spacing gets smaller and smaller, so you want a correlation length like that in physical units. Your lattice spacing is initially this much. Later on it becomes this much. Later on it becomes this much. So if you want the same physical correlation length, the correlation length in lattice units has to get smaller at precisely that rate, right? Such that your physical correlation length is the same. So the physical correlation length is fixed by this mu naught. Is this point clear? Mu naught is the physical mass scale of the theory. So the physical correlation length in angstroms or meters is basically 1 over mu naught on dimensional grounds. So that's a fixed number, physical correlation length. And this is what I want. So if I want my lattice to get smaller and smaller and smaller, I have to choose my correlation length to become larger and larger and larger so that the physical one is the same. Is this clear? So let me put it another way. If lambda naught is 1, and I want, suppose your correlation length you want is 1 angstrom, and my lambda naught is 1 angstrom, then I want C is 1. So I want C, let's say, is 1 angstrom. So if lambda naught corresponds to 1 angstrom, then C is dimensionless, C is just 1. But if I want lambda naught to be 0.1 angstrom, then the dimensionless correlation length has to be 10. Only then your physical correlation length will be 1. If your lambda naught is 10 to the power of 20 GeV inverse, then your physical correlation length will have to be huge, almost very large, I don't know, 10 to the power of 80 or something, let's say, in those units, to get C is 1 angstrom. So that's what's happening here. So as you make your lambda naught larger and larger, your correlation length has to be larger and larger, which means you have to tune your R naught such that you lie on some curve like this. Okay? So these curves are designed to give the same physical correlation length in physical units. So this is the canonical trajectory. If you start with some point here, typically some point, let's say you start with this point, so this is your h naught. This defines h naught, remember. So you're starting with h naught with lambda naught equals 10 and some h naught. Then you do a RG trajectory. You follow the RG analysis and you go to this, something like that. Okay. So now your theory, when you say theory, the theory lies on a trajectory. Okay, the theory lies on a trajectory means you have some initial lambda naught, the cutoff of your theory. You do an RG trajectory and you flow to the infrared and you get some new Hamiltonian here. So all along here you get your various HTs. All these theories define the same physics. They all have the same physical correlation length. Okay? So you fixed your correlation length by your starting point, and then you do your thing and it goes there. Okay? This is not continuum limit because this is only good for lambda naught up to 10. I can't go beyond this. So,
Each of these horizontal ciphers constant
Yeah.
are canonical surfaces.
no, the definition of canonical surface is just your the h naught. It's just this C is what I'm calling the canonical surface. It's a set of interactions which is parameterized by R naught and U naught as a function of your lambda naught, which you choose. This is your choice. It's not given to you by any trajectory. This is your choice, okay? So you have to tune it. You have to tune your R naught. Given a lambda naught, you have to tune your R naught to some point here, which gives that C. If you choose some other lambda naught, you again have to tune it to get that C. So that defines your canonical surface. And taking the continuum limit means finding this canonical surface, what should it do as around here? What should the values of R naught and U naught be when you go all the way back? Okay? So you can see now that if I want to take lambda naught equals infinity, and I want a finite mu naught, Xi had better be infinite. Okay, if your cutoff is practically 0 and you want 1 angstrom correlation length, then in units of that cutoff, your correlation length had better be infinite. Otherwise, you will not be able to take a continuum limit. So you have to end up on this surface. There has to be a critical surface when you take your theory to that end. So what are the typical trajectories like? So now we know how the flow looks like. So typically, if you start from here, you'll do things like that. This will be your typical trajectories. We have already seen that. Okay? So if you now define your low energy Hamiltonian as the one defined by Xi, remember we said we'll iterate till Xi is 1. So this defines your theory at low energies. Okay? So if you start with this, you'll get that theory. If you start with this, you'll get that theory. If you start with this, you'll get that theory. If you start with this in the limit, you'll get this point. Okay? You'll go along this trajectory, and so this is that famous trajectory we call the renormalized trajectory. Okay? So all these flows are, when you close the critical surface, they become parallel. The velocity is like this. Right here, the velocity is 0, so it can turn around and it goes off. So this is the asymptotic solution. Okay? So these points, so the renormalized mass is, finally, what is the renormalized mass? It's just lambda naught by R naught. This is what you choose it to be. Okay? So if you want, so I've given some names here. So this is the point 4. So I've got a curve like this. So this is a curve A. So this point is ht of 4, where lambda naught starts at 4. This point is ht 10. This point is ht with lambda naught is infinite. Okay? What else do I have to say? Yeah, so for the for the particular choice of mass, when you read c equals 1, you have some value of the effective. I mean, you have this is the value. So this is your canonical surface. This surface has a given lambda of t. So if you start with lambda naught equals 10, you go along this. You follow this to get the value of lambda. Okay. And this gives you that. This gives you that. So it just means that when you start from here, you have to do a lot more iterations to get the same value of the cutoff. So this and this are all on the same C surface, but it's quite a different interaction. The value, so what we are plotting here is in the space of interactions. So the value of the interaction here and here are all very different. The effective Hamiltonians are different. But the one that you get from the starting with the continuum limit is this one. Okay. Now this is a highly simplified, picture which I've drawn only 2 dimensions. But this trajectory, as I said, ht is a very special Hamiltonian. So getting this point involves tuning an infinite number of parameters. So this trajectory is very special. So if you want, you can define your theory, renormalized continuum theory, to lie on this trajectory. Okay. So at t equals minus infinity, which in the UE limit, it looks like this theory. T equals plus infinity, it looks like that theory. And in between, this is a trajectory. This trajectory is a very special trajectory. You cannot get this just by tuning. You have to get this by tuning an infinite number of values. This is not what you usually do. What you usually do is to start from some thing and then keep adjusting your parameters, these 2 parameters, to define this canonical surface. You don't ever worry too much about this trajectory. Okay? So typically your renormalization will involve just fixing R0 and U0, which is your starting point, on this trajectory. But if you had the ability to tune, instead of doing this, you could have just defined your couplings to lie on this curve, and that would be your theory for all values of momentum. If you knew what this trajectory was exactly, you could just live on that trajectory and don't have to go through this process of doing all this. But effectively, if you start with this and do that blocking, you will end up with that special ht. Okay. So just a few comments. So as I said, this point and this point have the same physics. This point and this point have the same physics. This point and this point have the same physics. This point and this point have the same physics. So this is the low energy version of your continuum theory. So in this theory now you can calculate correlation length, and in principle you can, if you know this Hamiltonian, you effectively taken your lambda naught to infinity. The theory is defined for all values of, because this, to go from here, see, to go from here to here is just a finite number of blockings. To go from here to here is an infinite number of blockings. So you can work back in principle an infinite time to get your original UV theory. So it's defined as that's the continuum lambda naught equals infinite limit. So when I said this is the simplest topology, remember I said you choose R0 as a function of lambda naught for a given U0. But U0 is not a free parameter, because in all these theories, in the Wilson-Fisher theory, it flows to the fixed value, which is some U star. So really you only have one parameter to tune. You could do this, instead of doing it about this point, you could do it about, say, the Gaussian point. In the Gaussian point, you would actually have two parameters to tune. Okay? You would have both lambda naught and u naught. So in that sense, the 5-4 theory, that's why we usually have to tune two parameters. But the 5-4 theory, in D less than 4 it's good, but in D equals 4 we don't know what this existence of this fixed point. So okay, so to summarize, the basic requirement for taking a continuum limit is you should have a critical surface and one fixed point with at least one direction, relevant direction which you can tune. See, if you're sitting right here, right on the critical surface, your correlation length is strictly infinite, then you get a massless theory. That's, in some sense, not what you want. You want to get a massive theory in the continuum limit. You want a massive scalar field. So you have to define it as by this limiting series of limiting trajectories where this mu is kept finite as lambda naught goes to infinity. If you just took mu equal to 0 exactly, then you would be exactly at the critical surface and you'd be just sitting there. There's nothing to do. That's in some sense. So if you want to take a continuum limit with massive theories, this is what you have to do. You need a fixed point about which to do this structure, and your theory in the U, when you go to higher and higher lambda naughts, it should flow to the, there should be a critical surface where C is infinite, and if you have this fixed point here, you're guaranteed that correlation lengths functions are well defined. We calculated that. We said it's governed by that fixed point Hamiltonian. So this Hamiltonian will govern your correlation lengths. You'll have a well defined limit as lambda naught goes to infinity. So this is
Lambda 0 equal to 2, we have many theories, right?
lambda naught equals 2. Yeah.
Intersecting points, right?
Yeah. So this theory is your could be one of your starting theory. This theory with lambda naught equals 2 is equivalent to this theory. So here you in principle came from a higher cutoff. This theory came from a still higher cutoff. Compare means the physical correlation lengths you calculate will be different.
It's better that I have one theory.
No, so what are we doing here? We're saying what is this process of taking lambda naught to infinity? So you have to start with some finite lambda naught and see how you should change your parameters to take lambda naught to infinity. So what we're saying is you should follow some trajectory like this as lambda naught gets larger and larger, such that you reach some critical surface and start from that point. That will define a continuum limit. So I mean I could just start from here and define a theory, right? But this theory I cannot take lambda.
Those points, the leftmost one,
Yeah.
as far as I can go, is the best.
This defines the continuum limit of the theory. Right. That's where this renormalized trajectory intersects the C equals 1. So now there are some issues about multiple fixed points. We'll do that next time. So this is basically, now we've gone to the field theory continuum limit, and I use the word renormalization, though I didn't use it in a perturbative sense. What I'll do next time, I'll talk about this work of Polchinski, where he writes down this exact RG and shows, at least I won't do it in detail, but shows how what the calculation looks like in a continuum. So not in this perturbative way. So how do you see, in perturbation theory you have all these divergences, and then you define renormalized parameters and summarize them in terms of some running scale and renormalized parameters. And it seems sort of miraculous that everything can be summarized into some finite number of parameters. But what Polchinski shows in his argument is that it's actually perfectly natural when you think in this language. It should have been obvious that it can be done. Okay? So we'll talk about that next time.